All right, well, welcome to CC Colloquium for 2/2/22, February 2nd, 2022. Fun date. And I think we have a fun talk coming up. Certainly the setup is a little bit fun here. James Keane is here with us, and Jim will introduce him in just a minute. We're having fun with Star Trek backgrounds here, getting our full Trek nerddom out. There are no announcements that I'm aware of, unless somebody has an announcement they want to share. I'm not seeing anything. And so I will turn it over to Jim to introduce our speaker.
Okay, thank you. I'm sorry, I don't have a Trek background. I'm not doing what the cool kids are doing. Sorry. Hey, everybody. Jim Bell here, professor in CC. Delighted to introduce James Keane, Dr. James Keane from JPL, planetary scientist and geophysicist, planetary geophysicist. It looks like you double majored in astronomy and geology at University of Maryland, College Park, which is awesome. It's a great, great pedigree for planetary science. And then got his master's and PhD just down the road in Tucson at the University of Arizona. And James studies the interaction from his website, studies the interactions between orbital dynamics, rotational dynamics, and geologic processes on rocky and icy worlds across the solar system. And he does more than just write that on his website. He actually writes papers on these topics, and went and looked at his CV, which you can get at from his JPL website, and it's just super impressive diversity of kinds of objects that he's been writing about or publishing on, preparing publications on, series, the interior of Io, the interior and dynamics of the moon, as well as small bodies in the distant outer solar system like Arrokoth that he's going to talk about today. So he's been involved in a number of space missions like GRAIL, the lunar gravity mission. He's been involved in a proposal for an Io orbiter mission that hasn't been chosen yet, but I know a little bit about it. It's a great idea. We need to study Io up close, of course, and New Horizons that we'll hear a lot about today in his presentation. And another thing I think is cool about this person is that in addition to being a scientist, he's also a really, really good science illustrator and science communicator. And many of you may have seen some of his drawings and illustrations that have accompanied both scientific research papers as well as sort of public outreach kinds of products. James, I don't know if you're going to plan to share any of those in your presentation today. Will you be showing some of your own work?
A couple will come in. They always do.
Great. That's great. So without further ado, then it's really wonderful to be able to introduce James and share his title, which is Geophysics at the Edge of the Solar System, New Horizons Flyby of Arrokoth. Welcome. Take it away.
Thank you. Share the screen. Oop. Interrupt me if it's not working. But good. Thank you for that. Good. Great. Thank you for that great introduction. I'm really happy to be here, at least virtually. I'm sad I couldn't come in person. But someday in the not too distant future, hopefully I can swing by ASU. And yeah, as Jim said, today I'm going to talk about Arrokoth. It's one of the objects of many that I have studied across the solar system. But this one I think is fun to talk about because it has a nice blend of both exciting science and also an exciting story to tell about its discovery and flying a mission past Arrokoth. And so the best place to start with that is actually to talk about the mission. And so the New Horizons mission was a mission selected in the early 2000s to go to Pluto. It would be the first spacecraft to fly by Pluto. Here it is under construction. It's not a huge spacecraft. It's not something the size of Cassini. It's pretty small, about the size of a baby grand piano. You can see the people to scale. And it's a very trim, lightweight spacecraft because they had to launch it really, really fast to get to Pluto in a reasonable amount of time. The spacecraft itself has a small number of instruments. I've listed them all here on the screen, but the one I'll be showing data from the most is the LORRI camera, which is the high resolution, just a black and white panchromatic camera designed to take images from far away. And then there's also color imagery coming from the Ralph instrument. But then there's a whole suite of other instruments that do things like composition or detect particles or dust. And they've all provided a lot of interesting results over the years. So here's New Horizons before launch. On the left, you can see it being placed into the fairing. There's a person in a clean suit down there for scale. The spacecraft is the gold part on top, and it's sitting on this pretty hefty booster. On the right, it's stacked on the Atlas V rocket that later launched it. For scale, there's a person up here next to the fairing. I had to search to find a person in that. And since it's a spacecraft and it launched, you feel that you're obliged to show cool videos of rockets launching, because what cooler thing is there? New Horizons launched in 2006 when I was actually graduating high school, to date myself a bit. And here it is taking off. New Horizons launched exceptionally fast from the Earth. It flew all the way to Jupiter in about a year, which if you compare that to missions like Galileo or Cassini, or even forthcoming missions like Europa Clipper that will go to or past Jupiter, is very, very fast. And so here's a cartoon sketch of that trajectory. Launched in 2006, flew by Jupiter in 2007 for a rendezvous with Pluto in 2015. And then it flew past Pluto into the Kuiper Belt. So some quick little glimpses from its journey. Here it is flying past my favorite moon in the solar system, Io, which orbits Jupiter. You can see a lovely volcanic plume over the dark limb of Io. And it zipped by out to the outer solar system and quickly closed in on Pluto. Here's a distant view of Pluto from New Horizons. The resolution on this, when it was still many weeks out, greatly surpassed what we had from Hubble, or what we can even still get from Hubble. And of course, New Horizons showed Pluto to just be a tremendously beautiful and geologically interesting world. The encounter hemisphere is dominated by this gigantic glacier with floating icebergs of water ice. The glacier itself is convecting solid nitrogen and other exotic ices that are gas here on Earth, and then cratered terrains outside. And so we learned a lot about Pluto. I'm not actually going to talk much about Pluto today, because New Horizons then flew past. This is a view back looking at Pluto. One of the actual surprises of the Pluto encounter was the extensive atmosphere and haze around Pluto. You can actually see layers in the haze. And New Horizons zipped on, having completed its prime mission. The main goal of the mission was to get to Pluto and do the first reconnaissance. After that came the New Horizons Kuiper Belt Extended mission. And this is where I start to get involved in the mission. So it was always the intent of New Horizons to visit other objects in the solar system in the Kuiper Belt if possible. However, when it launched, no such objects were known, or at least not known on its trajectory, I should say. And so in order to do a rendezvous with another object, you had to actually find it. And so an extensive search campaign occurred in leading up to the Kuiper Belt Extended mission, looking for objects. And many people on the New Horizons team spent countless nights in ground-based observatories hunting for Kuiper Belt objects in the sky in the direction that New Horizons was flying. It was exceptionally hard because New Horizons, turns out, is flying into the Milky Way on the sky. It's one of the densest regions with lots of background stars. It's very hard to find small faint things. And so it ended up taking Hubble to find what ultimately became named Arrokoth. And so here is the sequence of discovery images from Hubble showing Arrokoth, which at the time was called Potential Target 1. They discovered a handful of, where's it going? A handful of small objects that New Horizons could have rendezvoused with, and they ended up selecting Target 1. Shortly after, it had an informal designation that might pop up every once in a while, which is 2014 MU69. And then it was named officially, actually after the flyby to Arrokoth. So throughout this talk, I'll refer to it as Arrokoth. Now, once this actually gives a good sense of where you're trying to hunt for it. These are actually images from New Horizons, from the LORRI camera, when they first were able to detect Arrokoth. So Arrokoth is this thing in the circle, zoomed in over here with background stars masked out. And you can see it's just swimming in background stars. So we had very little information about Arrokoth before the flyby. Here's a schematic of where it is in the Kuiper belt with respect to Pluto. So it's quite a ways past Pluto. And in fact, those that study the Kuiper belt like to divide and classify the types of objects in the Kuiper belt by a variety of different ways. One of the most common is to look at the Kuiper belt in terms of the orbits of each object. And so here's a plot showing basically these colored dots on the screen. The horizontal axis is semi-major axis, so that's distance from the sun roughly. And the vertical axis is the orbital eccentricity, so how elliptical the orbit is. And each colored dot or plus on here is a Kuiper belt object. Pluto is in this cluster of black square or black pluses. It's in a 3-to-2 resonance with Neptune. That's what these numbers mean. Arrokoth is down here, close to 45 AU. And it's this type of object called a cold classical Kuiper belt object. It has a large semi-major axis, but very small eccentricity, and also a very small inclination. Those numbers are shown on the screen, which hopefully this is not blocking the screen. Oops. Sorry. So it has a very low eccentricity and inclination, a very distant orbit, takes about 300 years to go around the sun. And what's important is that low eccentricity, low inclination means that Arrokoth has basically sat at the edge of the solar system for all of solar system history. That's different than a lot of these other objects that have high eccentricity or are stuck in these resonances. A lot of these higher eccentricity and also higher inclination objects, they got scattered off Neptune and other planets. And so they've changed their orbits a lot over time. And we think that these objects like Arrokoth, these cold classical objects, are some of the more preserved ancient objects in the solar system. I didn't mention it, but cold in this context is a reference to the dynamical state, not the actual temperature, although all these things are very, very cold. So after its discovery, I mean, we knew its location in the solar system. We knew its orbit pretty well from Hubble. We knew some information about its size. We knew it was roughly 20 kilometers in diameter, but that's about it. It's so distant, so small, so faint, that it's hard to do a really thorough characterization from the ground. And so one of the things that really helped set the stage and allowed the New Horizons team to plan their mission was a set of ground-based occultation campaigns. And so that's what these figures on the screen are showing. This big picture is showing one of the occultation telescopes that was set up in South America for one of these occultation campaigns. And so this was work led by Mark Bowie. Mark Bowie actually has a paper out or coming out very soon about this. It's not already out, detailing all the work that went into this. And so what you're doing with this is, we know where Arrokoth is in the sky, and every once in a while it will pass in front of one of these background stars. And that will cast a shadow on the Earth in a very narrow band. So on this globe plot here, this horizontal line, that is the shadow. It's actually greatly exaggerated on the scale here, of Arrokoth crossing the Earth on a given time, date and time. And so if you go and place telescopes in that path, so here's a map zooming in on the location in Argentina where they did this, place telescopes in a swath or like a net, you can use those telescopes to monitor that background star and see if it dims out, see if you get caught in the shadow. And from that, you can learn information about the shape of Arrokoth. And so here are photos from shortly after the most successful campaign. They actually did several of these occultation campaigns. This is Mark Bowie holding up 5 fingers because they got 5 occultation detections during this, which is just astounding. Here they are analyzing data. And here's real data showing this occultation. So the star in the center of this frame is the star that Arrokoth occulted, and you can see it blinks out here for a few frames. And that is Arrokoth moving in front of the star. Now from that, this is the first sketch of mine that shows up. This is it's a sketch, but it's a sketch of real data. There were multiple occultation attempts done for Arrokoth. The first set, this June 3rd attempt, they actually missed the location of Arrokoth. This is it's very easy to miss these things because you have to be extremely precise in your location on the Earth and your knowledge of the star's position and Arrokoth's position. And over the course of this, our knowledge of the position of Arrokoth was sufficiently imprecise to make this very challenging. By the end of the occultation campaign, we actually greatly improved our knowledge of Arrokoth's location in the sky. So the first set of chords, they missed it. There was a later attempt from Sophia over the Pacific Ocean, which thought that they detected something, this little blip of a shadow. But that Argentina campaign was this, where each line is an observation of the star from a given telescope. And so these ones where there's a complete line, they didn't see the shadow pass in front, and over here they did. And so you can immediately start to figure out something about the shape of Arrokoth, its size. But even in these early days with this data, which is a lot of data, way more than we have for any other object in the Kuiper belt at the time, we still didn't know what its actual shape would be. So I was making all these sketches of what Arrokoth could be. Is it a binary with 2 separate objects orbiting each other and we just happen to see them cross in front? Is it a contact binary? Is it something more akin to an asteroid potato? Does it have a satellite? What does it actually look like? And during the week of the encounter, I started to get way more creative with what I was imagining for these different shapes of Arrokoth. And it turns out the Arrokoth itself is kind of akin to some of these things that popped up, but it was quite a lot of excitement trying to guess the shape or determine the shape on approach. We even had folks like here 3D printing the shapes to explain aspects of light curves and what Arrokoth or what New Horizons might see. So here, that was all in the lead up to the Arrokoth flyby. And then on New Year's Eve and then day of 2019, New Horizons would have its close flyby with Arrokoth. So here's a schematic from APL. The yellow circle down here was a stand-in for the shape model of Arrokoth, because we didn't know it at the time. And New Horizons basically zips by. It's going 14 kilometers per second. And it's doing it at quite a large distance, about 3,500 kilometers. So it's very far with respect to the size of the object. And doing this requires a lot of planning. There were practice runs of the flyby using fake data. There were multiple plans developed with contingencies for what if Arrokoth has a satellite, we have to avoid it. What if Arrokoth has a ring and we need to miss it? And then once you decide on your trajectory, you have to plan out all your observations ahead of time, because it takes hours for the radio signal from Earth to get to the spacecraft. So you have to pre-plan everything, send your planned instructions, and let New Horizons execute them. And you'll only get data transmitted right before the flyby and then after flyby. So to give you a sense of scale, here is Pluto. Again, a lovely image from New Horizons collected of Pluto. And the sense of scale for how big Arrokoth is, zoom in on part of Pluto, one of those icebergs I talked about earlier, and put Arrokoth to scale on it. So this is a exceptionally well-planned flyby targeting something basically the size of one of the icebergs in the lake on the frozen glacier of Sputnik Planitia on Pluto. So now to the actual data. So the Arrokoth flyby happened very fast. Not just the spacecraft is moving by, but all the science operations was very focused in a short duration. Because Arrokoth is so small, New Horizons has to get really close to it for you to get actual usable in a geologist sense data. And so this is just 24 hours out to flyby. We're starting to get more than one pixel. The left is the raw data. The right is a deconvolved image or inferred shape of Arrokoth from the raw data. And since I'm waiting to like actually see the objects, here's a sketch that I did again before flyby, trying to interpret this. There was discussion about cracked M&Ms as being the shape of Arrokoth. And eventually we start to get more pixels. Here was, again, this is now only hours out from flyby. It starts to look like a dumbbell-shaped object. So we started drawing dumbbell-shaped objects. These things started ending up in press briefings as we were getting close to flyby. I was keeping a live dry erase board diagram of how the shape has evolved, again, on a very short duration. And then finally, the flyby happened, and thankfully it happened successfully without any hitches. New Horizons performed wonderfully. It collected all the data, including this image that we're looking at on the screen. I'm back here. This is the highest resolution view of Arrokoth that we received after the flyby. You can also see the Christmas tree because it was over New Year's. And it being in an operations room when all this data is coming down is, I can't overstate how exciting it is to see some things for the first time and just to be blown away because you have no idea what you're looking at. It leads to a lot of fun speculation about what these different things might be. What does this shape actually mean? What are each of these blobs on Arrokoth? And here, this is a little video I put together. This is actually all the LORRI frames that were downlinked shortly after the flybys. This is to give you a sense of the raw data that was transmitted down that we were working with. It's not a lot of frames because this is happening fast, and the spacecraft capabilities are limited, and you have to make choices about what data you're getting. But this is basically all collected in the span of a couple days and then transmitted back to Earth over the span of weeks to months. Now here is the same data, but now we've collated all, aligned everything. You can see Arrokoth as New Horizons approaches. Sorry, it's spinning because Arrokoth is spinning. It has a rotation period of about 14 hours. The figure on the right is the same, but it's scaled to make Arrokoth the same size in every frame. So you can see it starts blurry and gets more and more detailed because we're getting closer and getting more resolution. And I hope you're not hearing audio, but if you are hearing audio, this is a video constructed by the New Horizons team. It has a soundtrack that I have to listen to while talking to you, made by Brian May of Keane. This is all the data stitched together and interpolated in a very nice and artistic way, showing the same data, zooming in on Arrokoth with also a lot of the lead up. And it ends with the high phase image as we were looking back. So this is sort of the dusk hemisphere of Arrokoth. And here's the highest resolution view. So I showed this earlier in the background with a bunch of people. This is the data unedited. And this is just a beautiful image. It's and one of the things that's amazing about the New Horizons flyby of Arrokoth is just how precisely and amazingly targeted this whole event happened. So right here is actually the edge of the CCD. So this is the full frame image over on the right. So the way New Horizons works is we have to plan the whole thing, although we don't have precise knowledge about the location of Arrokoth. And so New Horizons is screening by. It's almost like you're driving by something, you want to take a picture, and you just point your camera out the side window and hold down and collect 100 images as you're flying by. And you have to point, hoping that you get the target, let's say a building, in the frame of view. And they did it. In one dimension, it cut it close, but they did it fantastically. New Horizons also acquired color data. Here's the raw color data on the left. The right is a superposition of the two. And I'll start to get into some of the geophysics of Arrokoth from now on. And critical to that is understanding the shape of Arrokoth. And so before we get into some of the modeling done of the shape, I think it's useful to show some of these image pairs that were constructed during the flyby. They're not the coolest looking animations, but they are useful to help your brain build its own intuition about the shape of Arrokoth. So by watching these, which are taken from slightly different perspectives, you can start to get a sense for the shape. This is another pair. Again, you can see Arrokoth rotating. The resolution is different because we're getting closer, but this also helps build some shape intuition. And so what I showed you in the last frame was basically what we had during the flyby. And that led to this view, this sketch that I did during the flyby, where we basically thought Arrokoth was this like snowman dumbbell shaped object. It led to a lot of constructions of actual snowmen, snow people, this beach ball version of it, clay versions of it, fruit-based versions of it. It's also the BB-8 model that we had. And that's the view that we had during the flyby. And that led to this first shape model that we have. This was actually made by Carver Beerson, who I know is in the audience. This is his shape model from during the flyby, where it started off as two spheres. And basically, over the course of time, as we've analyzed data, gotten new data, the shape model has gotten more and more sophisticated. For example, this one was made by Alex Parker, and where now it's got a neck, it's got some ellipsoidalness to the second object. And this is actually a scan of a clay model that was shown in a previous view. Mallory Kinzik basically was looking at images in a dark closet and sculpting clay to try to match the shape model. And we actually did calculations on this. This was a very exciting blend of science and artistry. I'll note the background here, each square is 1 kilometer square. The Golden Gate Bridge and naturally the Enterprise D are down here to scale as well. Oh yeah, here's the shape model. This is now John Spencer did his own clay model that it looked a little bit different. But all this, the shape model took a big turn when we got the last images of New Horizons down. They came down shortly after the flyby. And these are these high phase images that I mentioned earlier, where we're looking back at Arrokoth and we only see the illuminated limb. Most of Arrokoth is in darkness. And since New Horizons is doing its like drive-by photo taking, it captures Arrokoth and it captures all these background stars, and Arrokoth actually moves across the background stars. And you can basically do your own little onboard occultation campaign with this, where you find which stars get blocked out by Arrokoth at different times. And this is some of the most important information for actually constraining the thickness of Arrokoth, because it turns out it's quite flattened. This is the next iteration of the shape model. This one was made by Simon Porter, and you may be able to tell, I'll show some videos in a bit, but Arrokoth has gotten greatly smushed. The snow person got ran over. And for a time, it looks like they kept getting run over. has it gotten flatter and flatter. Some detail popped out as these models were basically adapted, made capable of doing shorter and shorter scales, puffed up a bit. And so this is a good, as I'm flipping through these, a good indication of the real-time work that's happening over the course of several weeks and months within the team, trying to understand the data that we got on only a few hours. Now, the last models were all sort of global shape models. Once we had all the data, there were other folks on the team, people like Paul Schenk and Ross Beyer, who do stereo analysis. So you take two images and can pull out topography that way. You only get it where you have overlap of the images. So you can only get like a face of Arrokoth. You don't get the whole body, but that's very useful for getting short wavelength stuff. You can start draping it on these global models. And these things kept evolving until we got to the shape model that we have today. And so that's this. This is the current shape model, the current global shape model, I should say, of Arrokoth. Sorry, I'm gonna have a drink of water. Oops. So this is the global shape model of Arrokoth. I'll just keep it on the colorful one. The red arrow in the middle is the inferred spin vector of Arrokoth. So again, it spins once every about 14 hours. We actually approached it from its south pole. If you follow the right-hand rule, that's where the arrow is pointing down. And Arrokoth, it's again 2 lobes. There is structure on it that we can resolve in the shape model. And the color that I'm showing here, it just shows the distance from any given facet on the surface to the inferred center of mass. And so this also is useful for seeing the rough size of the object. So it's about 18 kilometers or so from the center of mass to one edge. So about 30 kilometers along the longest axis. Now, once you have a shape model, geophysicists like me can start abusing them and doing all sorts of things, calculating out all sorts of geophysical quantities, whether they should or not. And so this is the first of them. So if we have a shape model, we can actually calculate out the gravity field across the surface. You basically calculate out the gravitational acceleration from every point within the surface or every shape within the surface. And that's this color bar and number across the side. So I'll talk about the density in a minute, but we expect the gravitational accelerations to be of order millimeters per second squared, so very low surface gravity. Arrokoth is also spinning, so there's centrifugal acceleration acting on the body. Basically, the further you are away from the rotation axis, the more you might want to be flung off the object. You're not completely, because these are all lower than the gravity, but they're not completely negligible. And if you were sitting on the surface, the total gravity or total acceleration you would feel is the sum of those two components, which is shown here. To give you a little bit more intuition, if you think about small bodies, the magnitude of the surface gravity that we expect on Arrokoth is comparable to other small 10 to 50 kilometer sized objects. Like here is asteroid Eros, Mars' moon Deimos, and 2 small moons of Saturn. All of these have surface gravities on order comparable to Arrokoth. Now, once you actually calculate out the gravity, you can start to imagine what it would be like to walk around in that gravity field. And the first data product I'm showing is an attempt to show that. That's this geopotential altitude. It's a kind of esoteric thing, but what it is it's describing elevation across the surface with respect to the gravity field. Think of it almost like a geoid. It's basically, if you were standing, say, on a high spot here, the blue points would feel to you as being lower. This is slightly different than the geometric altitude, where you're just measuring the distance to the center of the object. You can see that geometric altitude, it has a very large range, whereas the geopotential altitude has a much smaller range. So here it caps out at about 3 kilometers. So even though Arrokoth is this bilobate world with bumps and stuff, it's pretty smooth. It's hills only a couple kilometers tall on something that's 30 kilometers in size. If you take the geopotential altitude, you can take a derivative of it and figure out the surface slopes. And that's what's shown here. Blue is low slope, so it would feel flat if you're walking on it. Red are slopes close to the probable angle of repose, about 30 degrees. So they're like steep hills or cliffs. The black arrows show the downslope direction. So if something was just walking downslope or sliding downslope, that's the direction it would go. And so you can see material, if it was at, say, the equator of Arrokoth over here, it would want to slide up to the north or south pole of Arrokoth, or it would want to go into the neck over here. So this is useful if you want to try to understand some of the geology and see if it's consistent with movement of material on the surface. Now, all the plots I showed, the gravity, the slopes, geopotentials, they all depend on the density of Arrokoth, which we do not know. So normally when we go to a planet or small body, we can figure out their mass and density and gravity field by tracking either satellites that we put there or other natural particles and how they move in response to the gravity field. So I'm showing a video of the orbits of OSIRIS-REx, the spacecraft in the top left, about Bennu in one of its orbiting phases. So Bennu is a tiny little asteroid, much smaller than Arrokoth, but they were able to measure the density and gravity field of Bennu by orbiting it closely over time and tracking the spacecraft. And so as the orbit moves here, part of the reason it's moving is actually because of the gravity field of Arrokoth. So if you can measure that movement, you can figure out what's going on inside of Arrokoth. If you have a spacecraft orbiting, that's great. Another way to do it, again, at Bennu, if you have natural particles orbiting or on suborbital trajectories, like some of these particles that were ejected off of Bennu, you can track those and figure out the mass or gravity field of the body. And so for Arrokoth, part of the challenge is that New Horizons flew by really, really far away. This arrow compared to the size of Arrokoth over here is to scale. Arrokoth would be unresolvable on the highest resolution monitor. And so New Horizons is so far away, the force of gravity from Arrokoth, which is very small, is very, very low to the point of it being undetectable. So New Horizons could not directly detect Arrokoth's gravity. It was not even expected to, because it was just zipping by really far away. The only hope at directly getting the gravity field of Arrokoth would have been if Arrokoth had satellites. So if it had a small moon or ring particles or things orbiting, you could track those and figure out the density of Arrokoth. And unfortunately for us, no satellites were detected orbiting Arrokoth down to a pretty small size. This is a figure from the Spencer et al. Science paper where they put quantitative constraints on it. So all the things I showed you, they required a density for me to say anything. So how am I getting a density? Well, us geophysicists, when we don't have data, do dangerous things. And there have been a variety of groups trying to infer the density using less direct means. And so I'm going to show one in detail, the one I put a lot of thought into, and that's those slopes. So on the left is the slopes across the model of Arrokoth. Again, blue is flat, red is steep. And on the right is a histogram of those slopes. And it's all for this density. Here I put in 1,000 kilograms per meter cubed. So that's like kind of a nominal density for a large KBO or a comet. And it turns out for small bodies, if you change the density of the object, it will change the distribution of slopes. And the distribution of slopes will decrease the most when you actually are at the right density for the object. It's something that it's not immediately obvious why that works, but it is something that is observed to happen in asteroids and comets. So I'll restart this animation again. So you can see as I decrease the density, the distribution of slopes goes down, and eventually the density gets so low that this thing shoots up again. It gets so high at this 50 kilogram per meter cube density that subsurface material is basically unbound. It would fly off at the ends due to the centrifugal forces. But in the middle somewhere, there is a happy balance point. Here it is going the other way. And you can see if you're quick with your eye, that happens in this plot at around 300 kilograms per meter cubed. Now here's the same information I was showing in the last animation, just in a static frame. Here, density is on the horizontal axis. The surface slope is going vertically, so flat is at the bottom, steep is at the top. And the color indicates the fraction of the surface area in that bin. So this is like if I took a bunch of histograms and stacked them on their sides. And you can see that the mean slope or median slope goes down to a minimum around 200 to 300 kilograms per meter cubed. And if you follow the techniques used by the asteroid and comet community, you can put some quantitative constraints on the actual density using this. So using this approach, if you believe this approach, there's a big if in there, but if you do believe it, you come out with a density of Arrokoth that's only 235 kilograms per meter cubed. For reference, the pre-encounter assumption for the density was 1,000 kilograms per meter cubed. So this is very low. Now I've shown you one example where we've looked at slopes. There are other groups that have done this in other ways, trying to constrain the density. Some work by Toshihiro Bayashi is really, it's a really nice short paper. And basically they use the configuration of Arrokoth to place a constraint on the density. And they again find something between 300 and say 500 kilograms per meter cubed. This is another recent paper by Mao et al. Where they looked at the spin evolution and concluded that it needed to have a pretty low density given the rate of impacts in the outer solar system. There's also a constraint from the inferred strength of the body. So none of these are independently all that super strong, and even together, they're probably not conclusive, but there's a lot of suggestive evidence for Arrokoth having a very low density. And so what does that mean in context? Here is a plot with way too many things on it. On the horizontal axis is the size of the object. On the vertical axis, and both of these are on log scales, is the density. Arrokoth is the black point with the error bars that I gave it. All the pink objects are other Kuiper belt objects. So we have densities for Kuiper belt objects, mostly if they have satellites. That's how we infer the density. That's why there's a lot of pairs of objects here. They're all larger objects and they all have higher densities. Only a few have densities low enough or with uncertainties low enough that they overlap Arrokoth. But it's important to keep in mind that the objects that we sample from ground-based and space-based telescopes are in a different size domain than Arrokoth and other small bodies, like in about an order of magnitude larger. Comets, which are thought to originate in part from the Kuiper belt and other distant small body reservoirs, they, on the other hand, have the sizes of comparable to Arrokoth. But the pre-expectation for a comet density was something between 500 and like 1,000 kilograms per meter cubed. There are inferences for comets having lower densities, although these two, like Hartley and Borelli, those inferences were actually made using the slope argument that I showed for Arrokoth, so they might need to come with a grain of salt. The one I kind of find the most interesting are these yellow points. These are some of the small moons of Saturn, which we know pretty decently from Cassini flybys. And those can have very, very low densities as well. Some very confidently measured at like 400 to 300 kilograms per meter cubed, something comparable to Arrokoth. So there is some solar system precedent. And perhaps that suggests some similar nature or origin. Arrokoth, we think, was built together pretty gently, maybe not unlike the small moons being built in Saturn's rings. In the last few minutes, as I want to make sure that there's time for questions. Feel free to interrupt me if I need to speed up or slow down. I want to compare some of these geophysical quantities to the actual geology that you see on Arrokoth. So on the left is that highest resolution view, that LORRI image of Arrokoth. Some scale bars are on the bottom. This plot actually shows down here the direction of the sun and with respect to the reference frame that we use for Arrokoth. And independent from me and my geophysics brain, there are a lot of geologists on the team that have spent a lot of time looking at this image and other images and the compositional data, trying to map out different terrains across the surface and different patterns that we see across it. Like, for example, there's this large crater over here on the small lobe. There are small spots, bright terrains in the neck, in different bands across the surface, all sorts of very interesting things. Here is the shape model that I've been showing for the last 15 minutes, compared in the same viewing geometry, not quite the same lighting, but close to Arrokoth. And so it's important to remember here that the shape model that I'm doing all my calculations with is a global shape model with some stereo data on the encounter hemisphere. So like where you see these smaller scale structure, that's from the stereo model. It's not complete globally, and it has limited resolution. So if there are small pits, like some of these bright spots we think are small pits, if they're too small, they don't show up on this stereo model. So it's important to keep in mind when making this comparison. Here is the geopotential elevation. I've just draped my color onto the LORRI image. And you can see some very basic trends. The equator of Arrokoth, if you want to call it an equator, it's basically the edge of the image, is the geopotential high. The geopotential lows are the face of Arrokoth, which is surrounded by this weird annulus, and in the neck, this bright region. So at first glance, there's some correlations you can pull out here, like bright material is often found in geopotential lows, like the neck, like some of these spots in the large crater on the small lobe. But it's not perfect correlation. Like the large face is not filled with bright material. The bottom of this crater is not filled with bright material. And there are also bright spots in places that are maybe not geopotential lows, at least on a global sense. Here is a map showing the slopes draped on this. Again, if you expect material to move downslope, if you expect mass wasting to operate on this object, things would move from the equator towards the central face and potentially down into the neck or into the large crater. And if you stare at this long enough, which me and many others have, you start to see patterns, whether or not you should believe them or not. Sometimes bright features appear aligned with slopes, downslope directions, like this on the bright lobes. So you might imagine, oh, maybe stuff is moving down slope. Other times, and even right next to it, it's orthogonal to the slope. So that annulus is often orthogonal to the downslope direction. And for example, the neck is also, it's a relatively flat place in the bottom of the neck, but it's quasi-orthogonal to the slopes then. There are also places on the small lobe, which has a lot of interesting like crenulated texture, where things appear to be at breaks in slope. So there are patterns, but they aren't always consistent. So it makes it hard to interpret. There are all sorts of other data sets like this one, which shows the escape speed from Arrokoth, which for the sake of time, I am going to skip to get to some Q&A. But if you want to ask questions about what's happening around Arrokoth and how it affects the surface, feel free. There's some interesting patterns here. And let's see if I can easily, I'm gonna exit to just skip ahead. And so last couple slides, we have a lot of interesting inferences we can make about Arrokoth, and that's led to this schematic diagram, again, a product of my colored pencils during the flyby, where we think Arrokoth was born early in the solar system. Originally, these two lobes formed from a smattering of different particles colliding until they made two, which then gently combined to the structure we see today. They combine gently because the neck doesn't appear to be heavily fractured and broken. But between all these steps in this cartoon, there are so many questions that we still don't know. And it's really difficult to interpret a lot of the geology we see on the surface. So that's going to be subject for debate for a long time. My last, I think I have a couple slides. just to talk about what's next for New Horizons. So here is where New Horizons is today. This is the APL website updates this. New Horizons is at a stunning 52 AU from the sun, way past Arrokoth. It cannot, if it looked at Arrokoth, it is too far away and too faint to see it. But just because of that, it doesn't mean New Horizons isn't doing anything. New Horizons is actually being exceptionally productive in these spans between close flybys. Here is a slightly out of date image, but while New Horizons is flying through the solar system, it's actually looking at a lot of other Kuiper Belt objects from great distance. Now, it's great distance for New Horizons, but compared to observing them from the Earth, New Horizons gets to see them relatively up close and in different viewing geometries than you can see from Earth. So from the Earth, you're always looking at basically the sunlit hemisphere of these objects. New Horizons can look at them from a range of phase angles, which is very useful for figuring out things like shape. And with that, I'll end on my summary slide and just say New Horizons, it revealed Arrokoth to be a very interesting and exciting world. There's a lot of interesting geophysics happening, a lot of geology to explain, and we're still left with a lot of questions. And so it's going to take a lot of work, both looking back at the Arrokoth data and maybe having other spacecraft missions or other flybys to other worlds to really start to piece this together. The work that I showed here is actually in revision at JGR Planet, so you can read more about this hopefully in the coming months if you want more details. And with that, I'll stop. So thank you.
Great.
Clap, 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 clap.
Clap, clap, clap. Please put questions in the Q&A and we'll be happy to beam them over to James there, who's floating in space without a spacesuit. So I don't know how he's pulling that off.
I'm a Q.
There you go. So we got one question here so far. Hopefully there'll be others coming in soon. So Trevor Austin asks, is Arrokoth's shape thought to be common in the Kuiper Belt?
Yeah, it's a great question. So the Kuiper Belt has a lot of binary objects. I forget the exact fraction. I think the number that comes to my head at the top is like 50% or more, maybe 70%. It's quite large. Maybe Carver knows the answer, can throw it into chat. So, but the Kuiper Belt has a lot of these binaries that we can see them as being separated. It's very hard to determine when we just see one object if it's actually a contact binary like Arrokoth. It's hard to do that from the Earth. New Horizons with these distant observations of KBOs has actually helped us a lot with that. And I think, again, it has found about 50% of the objects that it is looked at where we didn't know if they were a binary or not are indeed contact binaries. And that's from doing light curve observations from New Horizons at higher phase. So we think that we're beginning to think that shapes like Arrokoth are not necessarily uncommon. But it's going to be very interesting to think about how that affects basically how we think of the rest of the Kuiper Belt. There are a lot of non-intuitive biases that come out of having shapes like that and how you interpret, say, telescopic surveys of the Kuiper Belt. If a large fraction are these contact binaries, it affects how you interpret size frequency distributions, even the very number of objects in very complicated ways. So I wouldn't be surprised if Arrokoth was quote unquote a typical KBO in its size. But right now we only have the one data point. So it'll be interesting to get more either from other flybys by Kuiper Belt objects or exploration of other small bodies as they come into the inner solar system.
All right. Other questions. Are any other encounters planned?
Yeah, so I didn't have a slide for that. Right now, well, not literally right now, but over the past couple of years, the New Horizons team has been searching for another flyby target. It is very hard because this target, as you saw, would have to be mini AU past Arrokoth, and it took a lot of Hubble time to find Arrokoth. So it's very hard to find objects. In addition, New Horizons is just booking it out of our solar system to the point where you get to say things like it is running out of Kuiper belt, it is through the densest part of the Kuiper belt. So there may not be as many objects out there, but the team is still looking, and it's part of their extended mission proposal that if they find one, that they have put together a plan to do it. The spacecraft is healthy enough and has enough fuel on board to basically do another Arrokoth flyby if they found an object like Arrokoth or something. But it's hard to predict what objects you're going to find, and if we'll find anything in this path.
How does it was an earlier one. Can you do occultation spectroscopy on Arrokoth?
Well, you could certainly do occultations. I don't know if I know what an occultation spectroscopy would.
I guess looking for looking to see if there's any kind of atmosphere, I guess.
Yeah, I mean, you could. I think you could. So there are a variety of other instruments on board Arrokoth designed to do atmospheres and plasma experiments. There was no detection of anything indicative of an atmosphere. There was no detection of extra dust in the environment of Arrokoth either. So I think it would be very surprising if Arrokoth did have an atmosphere. I mean, that experiment maybe you could do. But one challenge with Arrokoth, so that spin axis is actually pointing more or less right at Earth, pretty close to Earth. So if you did the occultation campaign again, you would probably get the same shape again because it hasn't changed its relative geometry much with respect to the Earth. So in terms of, I mean, if you did some sort of spectroscopic occultation, maybe you'll learn something new. But in terms of the geophysics, you probably won't learn anything new unless you wait maybe 100 years and do it when it's moved a quarter of the way around the sun.
So another question, we'll do just a couple more. Why are there variations in bright spots in bilobe shaped objects? Maybe why are there variations in brightness at all, right? What are we seeing there?
I would love recommendations. So there are other geologists on the team that have thought about this a lot more than I have. There are probably a variety of different processes at play on the surface of Arrokoth. Impacts can cause bright spots in the formation of pits. Kelsey Singer has published work about this, about looking at the pits of Arrokoth and trying to determine if they are craters or if they are pits of other origin. And so if they're not impacts, one other way that you might imagine forming pits is from sublimation. So if the ice within Arrokoth, which is probably a mix of water ice and more exotic ices, things like carbon monoxide and other things that again would be gases here at Earth, they might sublimate, turn to gas over solar system history, and they might form little pits, which we see on comets all the time. So that might be one way of creating bright spots or even dark spots, depending on the exact nature of that process.
But underlying all this, the surface is somehow altered a little bit compared to what's underneath due to radiation damage, I guess. And
yeah, we expect that the surface is probably reddened and weathered much more than the interior. Although I think that's probably more of an expectation based on any sort of inferences based on like crater ejector or anything like that, because there just aren't that many craters and not much conclusive ways to really probe the interior.
So last question, just kind of a slightly fun one. So some of us remember this object was originally called Ultima Thule or Thule. So why was the name changed and what does Arrokoth refer to?
Yeah, so Arrokoth, Ultima Thule was the informal designation given by NASA ahead of the flyby. It was not officially approved by the IAU. There's always some fun tension between Pluto, the Pluto cohort and the IAU. But it ultimately was, that name was not ultimately kept on. There was a little bit of concern about potential meaning of that name. You can Google about that. And so in the end, Arrokoth was chosen by the IAU and NASA working together. And Arrokoth, I think it's a cooler name, honestly. It means sky in the local, I forget the exact tribe, the Native American tribe that the land on which APL belongs, or the land that APL is currently located on. Sorry, my sentence got all jumbled. Arrokoth means sky in the native language from those who have the land on which APL is located. I'll look it up and throw it into the chat after. And so that is now the official name. That's all that we ever use. And yeah. Great.
Well, thanks for a great talk. I'm going to make my way down to the shuttle bay on the Enterprise there to open the door to let you in, to rescue you from the cold deep space. But thanks for visiting with us. Thanks for sharing a really cool talk about a really neat object. Really appreciate your time.
Much.
Thank you.
Awesome. Thank you, James. Take care.
Thank you.